Hello everyone, welcome to Insight Lens, the channel where we dive deep into the stories behind world-changing technologies. In today's video, we'll discuss one of the most powerful companies in the semiconductor industry, ASML, the giant that holds the key to EUV lithography and the future of advanced chips. In the semiconductor industry, the spotlight often shines on companies like Intel, TSMC, Samsung, or NVIDIA, the firms designing processors or fabricating chips. But behind the scenes, there exists a company far less visible to the public, yet absolutely indispensable to everyone: ASML. This Dutch company has become the undisputed leader of EUV lithography, producing the only machines in the world capable of operating at a wavelength of 13.5 nanometers, the gateway technology that enables the production of chips at 7 nanometers, 5 nanometers, 3 nanometers, and now pushing toward 2 nanometers. Without ASML, there would be no iPhone processors, no cutting-edge AI accelerators, no latest Gen CPUs. Let's look at the numbers. In 2024, ASML reported net sales of $28.3 billion and a net profit of $7.6 billion. Its order backlog stood at over $33 billion, locking in demand years ahead from fabs like TSMC, Intel, and Samsung. Each EUV scanner costs well over $150 million, weighs over 180 tons, and is built from more than 100,000 precision components. More than just a supplier, ASML is the single choke point of Moore's Law at the leading edge. While Nikon and Canon still sell DUV machines for mature nodes, when it comes to EUV, ASML has no rivals. Before ASML's rise, Nikon and Canon ruled lithography. Rewind to the late 1970s and 80s. As the US pioneered semiconductor manufacturing, Japan was rising fast. Supported by government policy and industrial discipline, Japanese firms became world leaders in precision optics and advanced manufacturing. Out of this environment, Nikon and Canon emerged as the dominant forces in photolithography. At that time, lithography advanced through stages: 436 nanometers, G-line, 365 nanometers, I-line, 248 nanometers, KRF excimer, and later 193 nanometers, ARF excimer. Nikon and Canon mastered these transitions, supplying scanners to Intel, IBM, Toshiba, NEC, Samsung, and others. By the mid-1980s, Japanese firms controlled nearly 70% of the global lithography market, effectively becoming the choke point of Moore's Law. But global politics intervened. The 1985 Plaza Accord forced the yen to appreciate, damaging Japanese export competitiveness. The US-Japan Semiconductor Agreement further pressured Japan's chip industry, particularly DRAM. Meanwhile, R&D costs for next-generation lithography soared, margins tightened, and the push for new wavelengths grew riskier. By the 1990s, cracks appeared. Canon slowly exited the high-end market, while Nikon tried to extend DUV step by step. They were still dominant, but innovation slowed. It was in this climate that ASML appeared in 1984, a small joint venture between Philips and ASM International. Early ASML steppers were late, clunky, and unreliable. Few took them seriously compared to Nikon's dominance. But ASML had something Nikon and Canon lacked: a willingness to gamble on radical approaches. This hunger positioned ASML perfectly for the next disruption, when 19.3 nanometer lithography reached its physical limits and the world desperately needed a breakthrough. By the early 2000s, semiconductor manufacturing had pushed 193 nanometer lithography to its limits. Engineers tried tricks like optical proximity correction and phase shift masks, but Moore's Law was running into the hard wall of physics. Attempts to use 157 nanometer f2 excimer lasers failed because new lens materials, environmental controls, and costs made the technology commercially unviable. At this point, the industry seemed stuck, but then came a bold, counterintuitive idea: immersion lithography. Instead of projecting 193 nanometer light through air, what if you inserted a thin layer of ultra-pure water between the lens and the silicon wafer? Because light travels slower in water, its effective wavelength shrinks, improving resolution and allowing finer patterns. At first, the idea sounded absurd. Competitors like Nikon and Canon dismissed it as impractical. Introducing water into a precision optical system risked bubbles, contamination, and catastrophic damage. But ASML decided to gamble everything. They partnered with TSMC, which was aggressively chasing smaller nodes, to turn this impossible concept into reality. In 2003, ASML unveiled its first immersion lithography scanner, capable of extending 193 nanometers into the 65 and 45 nanometer nodes, and soon beyond. The bet paid off spectacularly. Customers like IBM and TSMC placed major orders, while Nikon's commitment to the dead-end 157 nanometer path cost them precious time. By the late 2000s, ASML had seized over 60% market share in advanced lithography, overtaking Nikon as the industry leader. The immersion breakthrough didn't just buy time for Moore's Law. It positioned ASML as the company willing to take risks others avoided. Part 4. EUV, the moonshot of lithography. By the late 1990s, it was clear that even immersion lithography had limits. To reach 10 nanometers and beyond, the world needed a completely new light source. The answer was extreme ultraviolet lithography, using light with a wavelength of 13.5 nanometers, almost 15 times shorter than deep ultraviolet. But EUV was so radical that no single company or even country could develop it alone. In 1997, Intel and the U.S. Department of Energy created the EUV LLC, a massive research alliance pooling America's top national labs, Lawrence Livermore, Sandia, and Lawrence Berkeley, with major chip makers like Intel, AMD, Motorola, and Micron. Their mission? Prove EUV could work. The challenge was staggering. EUV light is absorbed by nearly everything, including air and glass. That meant no lenses, only ultra-precise mirrors coated with molybdenum and silicon, vacuum chambers to prevent EUV absorption, a new light source, tin plasma lasers generating bursts of 13.5 nanometer radiation, mirror accuracy at the atomic level, with surface defects less than 1/10 of a nanometer. At first, Intel planned to bring Nikon, its trusted partner, into the alliance, but Washington blocked it, fearing Japan would gain control of next-gen lithography. Instead, Intel turned to ASML, then still a relatively small Dutch company. The U.S. demanded guarantees. ASML must build facilities in the U.S. At least 55% of EUV components had to come from American suppliers. U.S. regulators reserved the right to inspect for technology leakage. Reluctantly but strategically, ASML agreed. In exchange, it gained access to the world's most advanced research backed by billions in U.S. investment. Nikon, excluded from EUV's future, was effectively left behind. By 2002, the alliance had published hundreds of papers proving EUV's feasibility in theory, but commercialization remained elusive. The machines were massive, fragile, and impossibly expensive. ASML, carrying the torch, needed both money and customers to survive the marathon. That set the stage for Intel's decisive move, a direct 15% stake in ASML, giving the American giant priority access to future EUV scanners. What looked like a lifeline for ASML was in reality the final blow to Nikon. From that point forward, Intel concentrated its bets on ASML, and the Dutch company's rise to monopoly became unstoppable. EUV was not just a technology. It was the moment ASML transformed from a scrappy challenger into the gatekeeper of the semiconductor future. The first EUV machines, engineering the impossible. After years of delays, cost overruns, and skepticism, ASML finally unveiled its first commercial EUV scanner in the mid-2010s. It was a technological marvel, combining breakthroughs across physics, materials science, and precision engineering. Each EUV machine was 180 tons in weight, requiring 3 Boeing 747s to ship. Composed of more than 100,000 precision parts sourced from hundreds of suppliers worldwide, priced at over $150 million per unit. At its heart was the most fragile light source in existence, EUV plasma, created by firing powerful lasers at droplets of molten tin, producing bursts of 13.5 nanometer light. That light was then reflected, never refracted, through a series of giant mirrors designed by Zeiss in Germany, polished so precisely that if scaled to the size of Earth, the tallest bump would be less than 1 millimeter high. Every aspect of the system had to be reinvented. Vacuum chambers to prevent EUV absorption, ultra-clean wafer stages moving at accelerations faster than a fighter jet, yet accurate to the nanometer. Thermal control systems ensuring the mirrors never warped under the heat of plasma bursts. When the first EUV systems shipped in 2017-2018, they were not just tools, they were gateways to the 7 nanometer, 5 nanometer, and 3 nanometer generations of chips. Companies like TSMC, Samsung, and Intel lined up, investing billions to secure production slots. Nikon and Canon, once giants of lithography, had no answer. Their last bets on older technologies had failed, and they could not replicate EUV's decade-long head start. From this moment on, ASML became the sole supplier of EUV lithography to the world, a position no other company has ever held in such a strategic industry. This was the crown jewel. With EUV, ASML didn't just lead the market, it locked the gates to the future of computing itself. By the late 2010s, ASML had achieved what once seemed impossible: total monopoly over EUV lithography. No other company, not Nikon, not Canon, not anyone could catch up. But monopoly also meant geopolitics. For the United States, EUV became a strategic choke point. Washington leaned heavily on ASML's commitments from the EUV alliance. Critical components sourced from U.S. suppliers like Cymer for lasers and applied materials. Oversight agreements ensuring no leakage to adversaries. When China's SMIC tried to order its first EUV scanner in 2018, Washington intervened. Then Secretary of State Mike Pompeo personally pressed the Dutch Prime Minister to block the export license. By 2019, The Hague complied. ASML could only sell DUV machines to China, not EUV. The restrictions escalated. 2020, 2021, the US banned Huawei from advanced chips, cutting off its smartphone dominance. 2022, new rules extended controls to DUV immersion machines as well. 2023, the Biden administration convinced Japan and the Netherlands to join export bans, tightening China's access even further. Meanwhile, TSMC and Samsung built entire EUV fabs, racing to 5 nanometers and 3 nanometer chips. ASML's EUV tools became the most sought-after machines in the world, its order backlog stretching years into the future. The geopolitical message was unmistakable. Controlling ASML meant controlling the future of AI, supercomputers, 5G, and defense systems. For China, this was the ultimate frustration. Even with vast resources, state-backed projects, and copycat strategies, they could not replicate EUV. Their top firm, SMEE, was stuck at 90 nanometer lithography, obsolete by global standards. EUV mirrors, light sources, and software demanded decades of expertise that could not simply be bought or stolen. A wave of brain drain saw Chinese engineers leaving for the US, Japan, and Europe, further weakening domestic progress. By the early 2020s, ASML was no longer just a company. It was a strategic fortress at the very heart of the US-China rivalry, with every machine delivery shaping the balance of global power. The EUV monopoly had transformed into something bigger, the semiconductor industry's ultimate weapon, and ASML held the trigger. By the early 2020s, the ripple effects of EUV were everywhere. Every sector that defined the future of technology now depended on chips made possible only through ASML's machines. AI revolution. NVIDIA's A100 and H100 accelerators, the backbone of generative AI, are etched using EUV at 5 nanometers and below. Without ASML, the AI boom of 2023-2024 could not have happened. Consumer electronics. Apple's M1 and M2 processors and Intel's Core i9 series rely on EUV for their transistor density and efficiency. These chips power billions of devices worldwide. Cloud and supercomputing. Hyperscale data centers running services like AWS, Azure, and Google Cloud deploy EUV-based chips for maximum performance per watt. Telecom and 5G. Advanced baseband processors and networking chips depend on EUV for miniaturization and speed. Automotive. Self-driving platforms from Tesla, Mobileye, and others rely on high-performance chips fabricated with ASML technology. The numbers are staggering. By 2023, over 50% of all advanced chips at 7 nanometers and below were produced using ASML's EUV scanners. By 2024, ASML's backlog reached tens of billions of euros, ensuring years of fully booked production. Over 30 fabs worldwide, including TSMC, Samsung, and Intel, relied directly on ASML to keep Moore's Law alive. In effect, ASML became the hidden backbone of modern civilization. Every breakthrough in AI, cloud computing, automation, and national defense ran through one choke point: the supply of EUV scanners from a single Dutch company. The world's appetite for smaller, faster, and smarter chips was endless, and ASML had become the sole gatekeeper of that future. From a modest Dutch spin-off in the 1980s, ASML clawed its way past Nikon and Canon to seize the undisputed crown of semiconductor lithography. Over 4 decades, it mastered both immersion DUV and the near-impossible EUV technology, a feat so difficult that no rival has even come close. Today, ASML is not just a supplier, it is a strategic fortress at the center of global power struggles. The United States leans on ASML to contain China's semiconductor ambitions. Europe relies on ASML as proof of its technological sovereignty. And every leading chipmaker, from TSMC to Samsung to Intel, cannot advance without ASML's machines. The lessons are clear. Don't put all in one basket. Nations and corporations who depend on a single choke point face existential risk. Speed is survival. ASML's success came from daring leaps when rivals hesitated. Immersion lithography, EUV, bets that changed history. And most importantly, technology decides power. In the semiconductor age, whoever controls the tools controls the future. For China, the EUV blockade is a reminder that money and manpower cannot replace decades of collaborative science and trust. For the world, it's proof that one company's machines can shape the destiny of nations. ASML didn't just build lithography systems, it built a new world order, one wafer at a time. And in this world, the future belongs to those who hold the light.